Hello and welcome to my YouTube channel ChemWiz. In this video, we are going to discuss a very important topic, that is the application of Huckel Molecular Orbital Theory for Allyl system. We will discuss the following points: Huckel Molecular Orbital or pi molecular orbital, secular determinant, Huckel Molecular Orbital energy levels, the pi bond energy and delocalization energy, the coefficients and the Huckel molecular orbital functions, physical representations of Huckel molecular orbitals, where we will discuss both the graphical and three-dimensional representations. Let's take one by one. This is the allylic system. It may be a cation, radical or anion. In all the three cases, the pi electrons will be delocalized across the three carbon atoms C1, C2 and C3. The general expression for Huckel molecular orbitals or pi molecular orbitals can be written like as psi is equal to A1 phi 1 plus A2 phi 2 plus A3 phi 3, where psi is the Huckel molecular orbital. Phi 1, phi 2 and phi 3 are pz atomic orbitals of C1, C2 and C3 involved in pi bond formation. And A1, A2 and A3 are orbital coefficients. Secular determinant. Formation of secular determinant is a very important step, since in allyl system there are three carbon atoms across which pi electrons are delocalized. So there will be determinant of 3 into 3 matrix. For making determinant, keep 3 points in mind. Every carbon is attached to itself. For that, put X. For a carbon attached to another carbon, put 1. And for a carbon not attached to another carbon, put 0. Now let's make determinant. For that, first consider C1. Since C1 is attached to itself, so put X here. And C1 is attached to C2, so put 1 here. C1 is not attached to C3, so put 0 here. Now consider C2. Since C2 is attached to C1, so put 1 here. C2 is attached to itself, so put X. And C2 is also attached to C3, so put 1 here. If we consider C3, C3 is not attached to C1, so put 0 here. C3 is attached to C2, so put 1 here. And C3 is attached to itself, so put X here. This will be equal to 0, where X is equal to alpha minus E upon beta. Alpha is the energy of an electron in 2p orbital, beta the interaction energy between 2p orbitals, which is always negative, and E the energy of a particular Huckel molecular orbital. This is a determinant of 3 into 3 matrix. Before solving it, we should know that the sign varies alternatively as positive, negative and positive. Now let's break it into smaller matrices. For that, first write X and then multiply it with 2 into 2 matrix, which can be found by ignoring figures in front of X. So the 2 into 2 matrix will be X1, 1X. The second place is negative and there is 1, so put minus 1 here and multiply with a 2 into 2 matrix formed by ignoring figure in front of 1. So it will be 1, 1, 0, x. The third place is again positive and there is 0. So put plus 0 and multiply it with 2 into 2 matrix formed by ignoring figures in front of 0, which is 1x 0, 1. These all will be equal to 0. Further simplification by solving 2 into 2 matrices will give x into x square minus 1 square minus 1 into x minus 0 plus 0 is equal to 0, or x power 3 minus x is equal to 0, or x power 3 minus 2x is equal to 0, or x into x square minus 2 is equal to 0. So there will be three values of x: 0, plus root 2 and minus root 2. Huckel molecular orbital energy levels. This equation can be rearranged as E is equal to alpha minus x beta. Since there are three values of x, minus root 2, 0 and plus root 2, so there will be three Huckel molecular orbital energy levels. Putting x is equal to minus root 2 will give E1 is equal to alpha plus root 2 beta. Putting x is equal to 0 will give E2 is equal to alpha, and putting x is equal to plus root 2 will give E3 is equal to alpha minus root 2 beta. Since beta is a negative value, so E1 is less than E2, which in turn is less than E3. E1 is bonding Huckel molecular orbital, E2 non-bonding, and E3 anti-bonding. Thus, we can draw the Huckel molecular orbital energy levels for allyl system like this. These are E1, E2 and E3. The pi bond energy and delocalization energy. Here we will discuss the pi bond energy and delocalization energy in all the three types of allyl systems. The energy levels are the same in all the three systems as discussed a little while ago, and can be redrawn like as. In allyl cation there are 2 pi electrons, so both will stay in E1. Before bonding, the 2 electrons will stay in E2. So total energy of 2 electrons before pi bonding will be equal to 2 alpha. Total energy of 2 electrons after pi bonding will be equal to 2 into alpha plus root 2 beta. So pi bond energy will be equal to 2 into alpha plus root 2 beta minus 2 alpha is equal to 2 into root 2 beta. In allyl radical, there are 3 pi electrons, so 2 will stay in E1 and 1 in E2. Before bonding, all the 3 will stay in E2, and total energy of 3 electrons before pi bonding will be equal to 3 alpha. Total energy of 3 electrons after pi bonding will be equal to 2 into alpha plus root 2 beta plus alpha. So pi bond energy will be equal to 2 into alpha plus root 2 beta plus alpha minus 3 alpha is equal to 2 into root 2 beta. In allyl anion, there are 4 pi electrons, so 2 will stay in E1 and 2 in E2. So in this case also, the pi bond energy can be calculated in the same way as allyl cation and allyl radical, and it will be equal to 2 into root 2 beta. Thus, we can see that in all the three cases, the pi bond energy is 2 into root 2 beta. If there is no delocalization, the system will be like ethylene and the pi bond energy will be equal to 2 beta. So, delocalization energy is equal to pi bond energy when there is delocalization minus pi bond energy when there is no delocalization, which will be equal to 2 into root 2 beta minus 2 beta is equal to 0.828 beta, which is a negative value as beta is a negative value. The negative value of delocalization energy suggests that the delocalization decreases the energy of the allyl system and thus increases stability. The coefficients and the Huckel molecular orbital functions. Let's rewrite the secular determinant we created for allyl system. Since the three coefficients are A1, A2 and A3, so we can write A1, A2, A3 multiplied by determinant of 3 into 3 matrix is equal to 0. So we can write the three secular equations. A1x plus A2 is equal to 0, A1 plus A2x plus A3 is equal to 0, and A2 plus A3x is equal to 0. For bonding level, x is equal to minus root 2. Putting x is equal to minus root 2 in the first secular equation gives A1 into minus root 2 plus A2 is equal to 0, or A2 is equal to root 2 A1. Putting x is equal to minus root 2 in the third secular equation gives A2 plus A3 into minus root 2 is equal to 0, or A2 is equal to root 2 A3. From these two equations, A1 is equal to A3. Applying normalization condition, which is A1 square plus A2 square plus A3 square is equal to 1. Putting the values of A2 and A3 in terms of A1 will give A1 square plus 2A1 square plus A1 square is equal to 1, or 4A1 square is equal to 1, or A1 is equal to 1 upon 2. So A2 will be equal to root 2 upon 2 and A3 is equal to 1 upon 2. We know that the Huckel molecular orbital psi is equal to A1 phi 1 plus A2 phi 2 plus A3 phi 3. So putting the values of A1, A2 and A3 will give the function for bonding orbital as psi 1 is equal to 1 upon 2 phi 1 plus root 2 upon 2 phi 2 plus 1 upon 2 phi 3. For non-bonding level, x is equal to 0. Putting x is equal to 0 in the first secular equation will give A2 is equal to 0. Putting the values of x and A2 in the second secular equation will give A1 plus A3 is equal to 0. So A3 is equal to minus A1. Applying normalization condition will give A1 square plus 0 plus A1 square is equal to 1, or 2A1 square is equal to 1, or A1 is equal to 1 upon root 2. We already have seen that A2 is equal to 0. Since A3 is equal to minus A1, so A3 is equal to minus 1 upon root 2. Putting the values of A1, A2 and A3 in general Huckel molecular orbital equation will give psi 2 is equal to 1 upon root 2 phi 1 minus phi 3. For anti-bonding level, x is equal to plus root 2. Putting x is equal to plus root 2 in first secular equation gives a1 into plus root 2 plus a2 is equal to 0, or a2 is equal to minus root 2 a1. Putting x is equal to plus root 2 in third secular equation gives a2 plus a3 into plus root 2 is equal to 0, or a2 is equal to minus root 2 a3. From these two equations, a1 is equal to a3. Applying normalization condition, which is a1 square plus a2 square plus a3 square is equal to 1. Putting the values of a2 and a3 in terms of a1 will give a1 square plus 2a1 square plus a1 square is equal to 1, or 4a1 square is equal to 1, or a1 is equal to 1 upon 2. So a2 is equal to minus root 2 upon 2 and a3 is equal to 1 upon 2. Putting the values of a1, a2 and a3 in this equation will give Huckel molecular orbital psi 3 is equal to 1 upon 2 phi 1 minus root 2 upon 2 phi 2 plus 1 upon 2 phi 3. Physical representation of Huckel molecular orbital functions. For that, let's rewrite the wave functions psi 1, psi 2 and psi 3 for three Huckel molecular orbitals of Allyl system. There are two methods for their physical representation, graphical and three-dimensional. Let's first discuss graphical representation. The Huckel molecular orbital functions of Allyl system can be represented graphically like as. We can see that as we move along the axis containing C1, C2 and C3, psi 1 continuously increases till it reaches maximum near C1. Beyond this point, it decreases, reaches to a minima, starts increasing till reaches to maxima near C2, then continuously decreases, reaches to minima between C2 and C3, again increases, reaches to maxima near C3, and then falls off continuously. The function psi 2 changes its sign at C2. This point is called node or radial node. The function psi 3 changes its sign at 2 points, one in the middle of C1 and C2 and other in the middle of C2 and C3. So there are two radial nodes in psi 3. Thus psi 1, psi 2 and psi 3 have 0, 1 and 2 radial nodes respectively. Three-dimensional representation. The Huckel molecular orbital of Allyl system can three-dimensionally be represented like as, where psi 1 has only one nodal plane which contains the axis having C2, C1, C2 and C3. This is common to all pi orbitals. Psi 2 has one additional nodal plane perpendicular to the axis, while psi 3 has two. If you look at psi 1, there is no center of inversion, so it is called ungeared U and also represented by pi U. Psi 2 has inversion center, so it is called G rad G, and is also represented by pi G. Psi 3 having no inversion center is ungirad U and is also represented by pi U. That's all in this video. Please subscribe my channel and press the bell icon if you like this video. Thank you very much for watching this video.